Okay, last Excel example for chapter 4 is example 415. So this time we're going to introduce Simpson's quadrature, Simpson's rule for approximating integration and under a curve and or of a function. And this is going to give us our result. We've previously tried trapezoidal approximation in Excel, which is just an approximation of the area under a function and or an integral of a function. But this time we're going to get a little bit more precise with Simpson's rule. So it's actually not too difficult to set this up in Excel, but you do have to tabulate your function. So this is a post driven into soil, and the diameter is given, and we have some information about the type of wood. It's Douglas fir. So we could look up the elastic modulus on that and in the back of the book, and we'll get our answer for that, the value, I should say. And we've got a diameter. And now this is interesting because it's loaded on top with 20 kilonewtons. That could be a sledgehammer, for example, right? And as it is loaded, then it's going to have a resistant force at the bottom to keep it in an equilibrium. And it's in soil that has frictional resistance. You may have had geotechnical engineering and seen something similar to this that varies from 12 kilonewtons per meter at point B along the bottom up to 4 kilonewtons per meter at the top, which is a 2-meter Y elevation, all right, below ground. So that can be drawn or represented as a trapezoid, as you see here, and the function can be derived from the trapezoid. So this trapezoid in these two drawings shows how the function is actually derived. So the loading forces are entered, 4,000 newtons per meter at Y2, elevation Y2. This is above a baseline of Y0 at point B. And then W, the loading, is 12 kilonewtons per meter at Y0. And I suppose we could call those W and W sub 0 and reverse the terminology, but it doesn't really matter. So the normal force then is 20 kilonewtons downward, and that is minus 20,000 newtons. So the height is 2, that's Y. The diameter is given. Let's get it into meters. And the area then is going to be 1/4 pi d squared. I have expressed it both in millimeters squared and meters squared. So the area of the soil loading is the trapezoidal area, 1/2 of base 1 plus base 2 times the height. So you can see that's 1/2 of, we're going to call base 1 and base 2 these loadings, 4,000 and 12,000 newtons per meter. Look at the trapezoid. And the height is 2 meters. So you can just see the bases here, kilonewtons per meter, right? So it's 16,000 newtons or 16 kilonewtons. So that's the area of the soil loading in kilonewtons. Equilibrium conditions require that the force up plus the trapezoidal area minus the force down of 20 kilonewtons equals 0. So we're solving that, and we end up with 4, all right, in the Y direction. So F is 4. That's the first part of the problem. Then the function of the distributed load is, you can see that here on the right. It's F plus 2Y times Y, and Y will vary, minus 20, minus P is equal to 0. All right. So that is important to be able to derive the function from the diagram that you see here and all of the loading conditions. All right. So we have the elastic modulus. And then we want to do integrations by Simpson's quadrature. So this is the function we're integrating essentially to get delta from A with respect to B, top with respect to the bottom, the displacement of the top of the post with respect to the bottom. That's the second part of the question. We need the compatibility equation, as you see here, integrated over the function from 0 to 2 meters. That's the height Y, right? So we know most of the terms of the function. So if we just set up a vector of Y values, and I used sort of arbitrarily 0.1 meters, right? So that's essentially what, tenth of a meter, so that's a centimeter, right? And we've got all of these values from 0 at the bottom to 2 at the top. And then the function is just, we plug in the function, right? It's 2y squared, so 2 times whatever the y value is squared, plus This is line 33, row 33. Minus 20, right? So minus 20 is the next term times, we're distributing here, right? I'm sorry. Let's look at take a break. Let's look at the function here to the right of the integral sign, right? 2y squared plus 4y minus 20. That's this function expressed as a quadratic, right? So for quadratic, Simpson's rule is an excellent approach to do this. So it's 2 times whatever the y value is squared plus 4 times the y value minus 20. So that is the function. So you can see how we've got that. 2 times the y value squared, right, plus I have F30 in there, right? F30 is 4, that's F, right, that we calculated, times J17. So J17 is going to be Y again, right, minus 20. So then minus B19. And I've used a dollar sign to fix the cell at 4 and the cell at minus 20. And then you just simply copy this down. Sorry about that. You just simply copy this all the way down, and you will get the function. Now, if we cared about plotting this function, we could. So I would do insert charts, and then probably something like this. Right? So what we're really trying to do is get the area under this function from 0 to 2, right? And that is an irregular shape. So we could use trapezoidal approximation and break this down into a number of trapezoids, but we'd be really just sort of eyeballing that, right? Or doing our best to approximate. But we don't need to do that. We can use Simpson's rule. And here's the general equation. We need to know the interval. The interval h between each successive measurement in the y vector is 0.1 here. Right? I could have picked a different one, but whatever it is, that's the interval, h, right? So then we go down to the first value has to be at y0, right, where the function is going to be just a constant, and all of the y squared and y terms will drop out. So then you'll go down 2 intervals from that, right, skipping 1, and you'll enter in an equation that looks like this. It's G37, so that's actually the interval, right, divided by 3, the Simpson's quadrature, rule of thirds here, rule of 1/3, times, and then I have K17. So K17 is the first value here times, plus 4 times the second times the third value, right? And then we're just going to copy this down, skipping over one interval each time and reiterating that equation, right? So you can see how it's set up in Excel. Then you just sum this column and you get the integration, right? So I got minus 26.667. So that I have to be careful here because I want to note that, the delta that I want, right, is the integral, okay, which we just talked about, right, times 1 over AE. You can see that in front of the integral sign, right? So 1 over AE is easy to obtain because E was something we looked up or was given for Douglas fir, and A was the cross-sectional area that we calculated. So make sure you're in the same units. I put everything in meters squared and PA, pascals, so that I could just have 1 over EA is equal to Newton to the minus 1. So 1 over EA, this number times the result of Simpson's rule, which is the integral from 0 to 2 meters, is delta. I got minus 2.59 times 10 to the 4th meters, but I want to express it in millimeters because it's a very small displacement. So it's minus 2.59 millimeters. That's going to be downward, okay, in that direction.